heading on, please. Turn the open side to the right, please. Open side to the right before putting your heading on. Okay, so last time we did this problem. Is it up there? Yeah, okay. We did the flux out of the wedge, right? And we did the bottom and the left, and the front, the back, the side, and the top, and all this. And then we did the top, this red, what I have kind of red, this ramp. In order to do that, we used our special case, the minus p gx minus q gy plus r, to avoid having to parameterize the surface and do the cross product, right? We said in that general case, when z is a function of x and y, and we parameterize as x, y, and then the function, we use the special case. And when we did that integral, we got, you guys got 5/6, right? You guys got 5/6. So I think you came up after class and figured this out. So what was wrong? And I said it was supposed to be negative 5/6. So did anyone else at the time or now resolve this issue? So what's going on here? So it has to do with, what did we say for this problem? Inward orientation. Inward orientation. So inward orientation for that top face would be what? What direction would inward orientation be? Yeah. Yeah, okay, so with respect to z, it would be down, right? So it would be downward. When we use the special case, that's oriented for z upward. Okay? So we did the integral right, we got positive 5/6, but now if we're going to say what's the flux with inward orientation for the whole surface, that's why it's negative 5/6. Does it make sense? And that's why the inward flux is indeed -1. Because we're going to take that special case would be for positive z, for flow in a positive z direction. And since we got a positive value flowing up, their inward flow would be negative, and that would be down. So that's what happened. So all these other ones, we set up the n vectors. We found all those n vectors for inward orientation, right? We said, n1 was 1, 1, -1, 1, and that was all. We already had that built in inward orientation. But this last one, we forgot to consider that we were using inward orientation. That would flip the sign of the integral that we found. So answer is -1. That integral, yes, is indeed positive 5/6. We changed the sign to do inward orientation, and then we get -1. Okay, questions on that? Yes, please. No, it absolutely matters. Outward orientation, we would have had all the opposite of these n vectors. These n vectors we wrote for inward orientation, for the direction for inward. So all these normal vectors to the planes would all have been opposite, and we would have kept the 5/6 if we were doing outward orientation. No, so it's kind of the reference is z. So outward orientation for this plane would be z up, because you're going out of the surface, out of the closed surface. And inward orientation for that plane would be z down. The special case is for z, positive z up. That's that special case formula that we used. And we got 5/6, but we want to do the whole surface with inward orientation, so we take the opposite of it. Is that better? Okay, good. Does it make sense? Okay, and so then I posted the video and I hope you watched it to help you with those examples of this one here. Doesn't it? It's smaller, it doesn't get bigger for me. I can't make it any bigger. Okay. So I posted this example here, and we wanted the flux through the closed surface, which is the cone, which I'm calling S1, and then the top disk at z equals 4, which I'm calling S2. So I'm not going to go through this for time's sake. We need to move on to get through everything. We need to move on, but I'll just quickly talk through it. You need to analyze this example and really go slow through it so you understand it. But here's parameterizing the two surfaces. The cone is going to be r cosine theta, r sine theta, r. Use r and theta to do that, and then the disk will be r cosine theta, r sine theta 4, because all z coordinates are 4. So that's the parameterization of our cone and our top disk, and then we're going to work through all the math, right? So we're doing f dot the cross product dr d theta for S1 and for S2. So the one thing that I mentioned in this is, should you do r cross r theta or r theta cross r? Well, if you do the parameterization or the partial derivative r cross r theta, then you get this. You get negative r cosine theta, negative r sine theta r. This is for the cone, by the way. And if you switched it, if you flipped it and did r theta cross r, then you would get the opposite of all your components would be the opposite. So the question is, which one of those gives inward orientation? So inward orientation means what about the z coordinates? If you're doing inward orientation on this cone, what are your z coordinates there? Positive, right? It would be up. You see that? So which one of these two would we pick to get inward orientation? The first one or the second one? The first one, right? The first one, because you have positive values for z. R is positive. So there's this question with the cross product of an r and theta, right? We don't have right-hand rule because it's kind of like theta, theta and r are not, they're like a different than rectangular coordinates. So the question is, should you do r cross theta or theta cross r? Well, if you want inward orientation, you want your z to be positive, and so you pick the one that has this positive z. Okay? So I did that cross product and worked through the flux integral. For that first one, you get negative 128 pi over 3. And then the disk, S2, the top disk. So I posted this on Blackboard. You're going to watch this, study this example. It's just doing the flux through the cone and then the flux through the top disk. Okay? There's a lot of subtleties and nuances on the process, so you have to watch it and work through it. Or try it yourself first and watch it. But then anyway, so then the total flux is going to be the negative 128 pi over 3 plus the 192 pi over 3. And then that's going to give you the flux of 64 pi over 3 was the answer to this one. Okay. So any questions on that? All right, so let's talk about something called flux density. Okay, there we go. So flux density. Flux density is the rate of change of flow of a vector field out from a given point. The rate of change of flow out from a given point in a vector field. So what we do to find that is you take a small closed surface around P, like a sphere is a good thing to do. And you're gonna do the flux out from that surface divided by the volume inside S. So it's a ratio of the flux out through the surface to how much volume is inside S. So a smaller volume, right? A smaller volume for the same amount of flux gives a higher density. Should make sense. And a bigger volume for the same amount of flux is less density, right? So the flux is less dense. So as you shrink their volume, and if you had the same amount of flux for a smaller volume, you'd have higher density of flux. All right, and then if it's a pointwise phenomenon, so we're going to take the limit as that volume goes to 0. So it's going to be that the flux around S as the volume inside S goes to 0. And so this gives us the idea of flux density, the rate of change of flow of the vector field out from a given point. Does the idea make sense? So the dense, so how concentrated is the flux is what we're saying, right? A high concentration would mean you've got a lot of flux for a little teeny volume around S. The more flux you have in a small sphere around S, the higher the flux density. So you can think of it as concentration of flux at a point. Okay, so here's a defining example. It gives us the idea. So let's consider the vector field x, y, z. And we'll consider the point at the origin. And we'll consider a sphere with radius a. So here's what we got. So we're at a point in the origin, and we got our sphere of radius a. And the vector field is x, y, z. So at any point x, y, z on the sphere, the vector field, the force of the vector is also x, y, z, right? Because of what the vector field is. At any point x, y, z, your vector is the vector x, y, z. And that's going to point radially away or orthogonal to the sphere, out from the sphere, right? If it's the vector x, y, z, it's really actually the same as you could have as a position vector. It would be the radius, or you could put it at that point where the force is actually applied. It'd be the same vector as the radial vector. So recall for constant flux, for constant F, the flux was just F dot S, right? F dot S was our flux formula. And so we could use, for the dot product, we'd use the product of the magnitudes times cosine theta. And so for any given sphere in this situation, in this vector field, for any given sphere on the origin, we're going to have constant flux on that sphere. Do you see that? All those flux vectors are going to be the same magnitude. So the magnitude of the flux is just going to be a, right? The magnitude of that vector is going to be the same as the radius. The whole area is the area of the sphere, 4 pi a squared. Theta equals 0 because the direction of the flux is orthogonal to the surface, which is the direction of F. So theta equals 0. So therefore the flux is just the product of the magnitudes times cosine theta is 1. So the total flux out the sphere of radius a is 4 pi a cubed. So the flux density, what we talked about earlier, then that's going to be the flux we just calculated divided by the volume around the point. So that's the volume of the sphere. And so what you see is it doesn't have to, the a cubes go away. So actually, in this case, the flux density is irregardless of the radius of your sphere. So you can make that sphere as small as you want, and you still get the value 3 every time. So that's the flux density of this vector field at the origin. It's 3. Any observations or connections to previous stuff that we've done? Seem familiar to something we've done before? Yeah, right. Okay. Right, yeah, so it seems like divergence, right? It's kind of like, what, expansion rate of change. That's what we're saying, expansion rate of change. So, what is the divergence of vector field F? Was it?
Just the sum of all the flux density.
Yeah, and what is it? So what is it? No, not triple integral. How do we find divergence? Remember? Yeah. Yeah, so we're going to do what? The divergence is just going to be the first component with respect to x plus the y component with respect to y plus the z component with respect to z, which is, in this case, 1 plus 1 plus 1 equals 3. So this is not a proof that flux density is the same as divergence, but it's just a defining example, okay? It's the easiest example that we can see that they're the same. Okay, it's getting good now. Any questions about flux density? Divergence. Yes, please.
So, because flux density is divergence,
Yeah.
is there ever a point where we're going to have like the limit of volume goes to 0, the flux over the volume? Is that even necessary anymore, in a sense? Couldn't we just go back to
Right, exactly. So this formula, this limit of volume goes to 0, this ratio, is getting to the heart of like what flux density is. But if you need to calculate it, it's often will be easier to use the divergence. Yeah, they're the same. Okay, well this is taking us somewhere here. So given a solid E with a boundary S, this is a closed surface, in a vector field F. Okay, so I've got this solid E, and its shell is S, right? Closed surface. We've been dealing a lot with those. So I'm going to look at one element of E, a box. So all throughout the interior of that solid, we can break it up into little boxes. And so here's the box. So it's just that little box is one of the boxes that makes up E, and so its dimensions are delta x, delta y, and delta z. And then we can take the value of we take the vector at that point, say PQR, right? So PQR is the vector of the vector field at that particular box. Okay, but across delta x, delta y, and delta z, we're going to have a slight change in those components of those vectors. So for instance, for the P, right? For the P component of that force, you might have a slightly different x component, so x naught plus delta x versus x naught, y naught, z naught. So as you move across that box by delta x, your P component might change a little bit, right? So flux density at this point, right? Our flux density is the flux through the small cube around that point over the volume of the cube. So, and what we say, divergence, right? Divergence would be the same as, let's see, flux density, flux. We have that little change in P times delta y, delta z. Similarly for the change in Q, similarly for the change in R. So delta Y, delta Z is this area right here, and so we're saying how much does P change times delta Y, delta Z would be our flux, right? It'd be our force times area, or vector times the area. This is perpendicular. We don't have to worry about dot product. It's just going to be the whole change times delta Y, delta Z, and similar in the Q and R directions, or the Y and Z directions. So notice what that is, right? The partial of P. So if we split this up into three fractions, and we take the partial of P with respect to X right there, the delta Y and delta Z's cancel out. And so what does that become? That becomes the partial of P with respect to X. Similarly, you get the partial of Q with respect to Y and the partial of R with respect to Z. And so that's why this is now proof. This is a proof of how flux density is the same as divergence. So you look at the flux in three directions. You look at the flux in the X direction, flux in the Y direction, flux in the Z direction. Set up your flux density, and you show that you get the sum of the partials. Yes, ma'am.
Why is the vector PQR placed in the middle of the box instead of
It's kind of arbitrary, right? It's just saying that at this location, right? If you're thinking about everything is small, it doesn't really matter, right? It's just saying at this location where I'm picking this box, there is some force vector. So I guess you're saying x naught and x naught plus delta x, that it should be like down here. Yeah. So when things get small, it doesn't matter. Yeah. So, but yes, that kind of with how I've written that here. Yeah, maybe it makes more sense to have that at that corner right there. Other questions? Okay, so this is showing that the flux density this is proving the flux density is the same as divergence. Okay, so then, given this, that the flux density is flux over volume, and flux density is also divergence, we can kind of change that around. So this is divergence. And solve for the flux. So the flux through one small cube would then be the divergence of F times the volume of the cube. And that's what I'm saying here. We're going to use this next. So all I'm doing is taking our flux density formula equals divergence, and then solving it for the numerator here. Flux out of one box then would be the divergence times the volume of the cube. Okay, so that leads us to what's called the divergence theorem. And I'm going to look at the sum of the flux out of all the little delta V boxes. Okay, and we're going to examine that in two different ways. Examine that in two different ways, the flux out of all the delta V boxes. And the first way is what I just said, right? The flux out of one box, we just said, would be the divergence times the volume of the box. So sum all those up. Is that fair? The other way is this idea that we've seen before. If we were to look at the boxes, adjacent boxes, and calculate all the flux individually out the closed surface of each one of those boxes, what would happen? Yeah, so yeah, this was in Green's theorem. So what will happen if I compute like we did in class last time? We computed the flux for the six-sided figure, right? And so say I did that for this and this one and this one and this one. And I'm going to sum all those amounts of flux up.
All the boxes which are touching internally will end up canceling out.
Right. So the face, say the face on this one here is going to be equal and opposite the flux to the face there because they touch. And same with this and this, same with the bottom of this one and the top of this one. Any two boxes that share a side, you're going to have equal and opposite values of flux for those sides. So they're all going to cancel out. And what's going to be left? What's that? Right, so all that's going to be left are the sides of those boxes that are on S, right? The ones that don't share another side. So you're just going to get, what are you going to get? You're going to get the sum of the surface integral of F for all the boxes, which you said. What we're going to get is we're going to get the flux, what? We're going to get just the flux out of S, right? F dot ds. So we can add them up all internally, one at a time, and sum those all up. That's the first way. Or we can see that they're going to cancel out, and what we'll end up with is just the surface integral, the flux of the shell of E. So how do we sum up the divergence of all those boxes? Right? That's going to be triple integral, right? That's going to be a triple integral over E of the divergence of F dV. So these are both of these are summing up the flux out of all the delta V boxes inside the solid. So therefore, they're equal. Okay. So the divergence theorem says that E is solid with a piecewise smooth boundary, and F is a smooth vector field. Then the flux out the shell out of S is the same as the triple integral of the divergence, which is, you think of that as summing up all the flux out of all the individual tiny boxes inside. Yes, sir?
Can you say again what you mean by smooth?
So just like no wrinkles. So like a smooth curve doesn't have a corner point. So that would just be like extended up into 3 dimensions. What would that be, right? So this is not smooth, right? Because you have a corner point. So in a surface, you can't have any like creases or wrinkles. So, what is this? Recognize what we have? Okay, so yeah, so someone's on Green's theorem. So, right, it's another fundamental theorem. And do you remember what our qualities of all fundamental theorems are? So we're going to analyze this for the commonalities to all fundamental theorems. Can you think of one thing that's common to the fundamental theorem that we see in this? Remember what we said? Okay, so what we said was the accumulation of lots of little bits where each one of those bits is calculated how? Using? Go ahead. Is that a hand? What's the key here? So this is a little bit of accumulation, and it's computed how? Using what? What's this? Oh, calculus students. Rate of change, right? Rate of change. Divergence is a rate of change, right? So we calculate all these bits of change, which is in this case flux, using the rate of change, right? Rate of change times little volume. And when you accumulate those all up bit by bit, that's equivalent to what? What's that? And so, yeah, what's the commonality there? F of B minus F of A. This is kind of like the F of B minus F of A side. So what do we say about that? It's like the net accumulation, right? Associated with what? Good thing we're talking about it. Associated with what for the solid E? The boundary. So, if you couldn't answer my questions, today is the day when you will be able to. Today is the day we learn it. This is all fundamental theorems of calculus. This is what they do. On the one hand, you can accumulate bit by bit using the rate of change, right? You can accumulate bit by bit using the rate of change. On the other hand, when you do that, you get an overall change, or you get an overall change, and that's associated with the start and the end, or in this case, the boundary of that thing, right? Learn it now. Learn it forever. It's the fundamental theorem, right? Now we're doing it over and over again. So every fundamental theorem we have, what we had so far? We had the fundamental theorem of line integrals, and we had Green's theorem, and we had the divergence theorem. All of those follow the same pattern. Any questions? So let's take a look at the examples we did last time, because the examples we did last time, we calculated flux through some closed surfaces, right? We did the wedge, the ramp, the wedge, and then we talked through that, but you're going to watch the cone with the closed cone, right? So that we were doing this. So now we have another way to compute the values of those flux. How can we do it? Triple integral to divergence, right? Triple integral to divergence. So let's see if we get the same thing. So let's go back to so we had this example here. Well, we spent like half a class doing this one, right? Okay, what was our vector field that we were in for that one? XY? Y squared? Z. Okay, very good. And this was this x equals 1? What plane was that? X equals what? Was it x equals 1? And then this was y plus z equals 1? And you remember the screen. It was all filled up. We had the 4 different plane sides, right? And then we did the 5th side. And so we found that to be what? What was our answer? -1? -1. So now we have another way to do that. What's the other way to do that? We could find, so alternatively, what does it equal? Right, so the triple integral over E of divergence of F. Now, -1 was for what? For inward orientation. So, if we get +1, By the divergence, will that phase us? No, that's just saying that triple integral was calculated for outward orientation, which I suspect it's going to do. Okay, so a triple integral, what's the divergence of f? Y? What else? Plus 2y? Plus 1. I'm already feeling like this is going to be a lot easier, right? And then now we have to just decide. So we have to do the triple integral. So we've got, right, our type A, B, and C. So I think easiest would just do type A. Type A starts with what to what? Bottom to top. So variable is dz. And so bottom to top is going to be from what to what? 0 to 1 minus y. Oh, I've never done this before. I hope it works. Okay. And then, what's the outside double integral? Projection into the xy plane, right? Projection in the xy plane, which is in this case is just a square, unit square. Super easy, doesn't matter. Do dx first, do y, doesn't matter. So I'll do dx dy. X goes from 0 to 1, y 0 to 1. So this is going to be 3y plus 1. So we're going to do dz first. What do we get? It's going to be 3y z plus z from 0 to 1 minus y. Is that right? I'm running out of room here. You guys seem way too bored for how cool this is. dz, dx, dy. Okay. So this is going to be 3y times 1 minus y plus 1 minus y. Did I get it right? And then 0 is going to make this 0. So what do we get here? 3y squared plus 3y minus y is plus 2y plus 1. 3y squared plus 2y, check my math, plus 1. Right?
Yep.
With respect to x, we're just going to get this back again, right? It's going to be this whole thing times x from 0 to 1, so we're just going to get it back. So it's going to be that thing with respect to y. Y cubed plus y squared plus y. Didn't work. What happened? We get 3?
No, that's it.
Negative 3y squared?
Yeah.
See? All right. So is it? You get 1. And so indeed, that was doing it for outward orientation, right? This found it for outward orientation, so positive 1. Had we done the surface integral for outward orientation, we would have gotten positive. Everything would have been opposite. We got positive 1. So check, verified, right? So we verified the divergence theorem for this solid in this vector field. Yeah, Justin.
Is there a way of knowing just by looking at it whether it's going to be outward or inward?
No, you decide how you're calculating it, right? And then the fact that it turned out to be positive with outward orientation means that the net flux is out. So you decide, and how you're calculating it, you decide whether you're doing inward or outward. We decided inward originally, and we got negative 1. So for inward orientation, negative flux means that that truly the net flux is out of the surface.
Does the triple integral of divergence just always find it outwardly?
Mm-hmm. Because outward is like positive convention, basically. Questions on this? Okay, so let's do the other one. So that cone, I think I showed you in class at the beginning here that it was what, 64 thirds? So this was cone. Is it just x squared plus y squared? And I think this was z equals 4. Square root, cones are square root. That would be a paraboloid. That's a cone now. Okay, your turn. So verify the divergence theorem. We already found that the double integral over s of this thing, f dot ds, was positive 64 pi over 3, I believe. Again, a really important example. Make sure you know all the details. Posted the video. And you're doing lots of these for web work tonight, right? Lots of flux integrals. Yes, please.
What was the force?
Yeah, what was the force field? Everybody, I can find it in a sec here. Y negative x z. So you're going to work on this while I take attendance. All right, check me. Here's my triple integral. Did you get the same thing? Did anybody get that? I don't know. I got 1. I got 2. I got 3. Okay, 4. Good. Check my math. Minus 64 thirds. 32 thirds times 2 pi. That's 96 thirds. Did it work? So who would have thought triple integrals are easier, right? Right? That's how it works with the divergence theorem often. Why? Because you often have to do this. The flux integral over the surface means multiple flux integrals because you have a piecewise surface, right? So oftentimes the triple integral of the divergence will be an easier calculation. So again, to verify the theorem means you do both sides and you show that they're equal. That's kind of what we did, right? We did it before, just the flux of the closed surface. Then we did it using the triple integral of the divergence. Using the divergence theorem to find, say, the flux out of a closed surface. Would mean doing what? If it said, use the divergence theorem to find the flux through S in the vector field, what would that mean? Do you parameterize the different parts of the surface and do f dot ds? Is that what that means? No, because then you're not using the divergence theorem. You're just calculating the flux. So using the divergence theorem would mean do this. Do the triple integral instead. Do the triple integral of the divergence by the divergence theorem. That's equal to, equivalent to the flux through S. So that's often the question you have to ask yourself. If you have to, is it easier just to do something directly or use the theorem? I mean, calculate something else, and then by the theorem, they'd be equal.
So you have rules of thumb of when you would want to use which.
No, it's just observation, trial and error. Normally, usually if you've got 3 or more pieces to a surface and they're not friendly, they're not rectangular, parallel to a coordinate plane, then probably it's going to be harder to do the individual surface integral directly. Okay, so you have those